6.3 step functions. We said in the beginning that the Laplace transform can handle equations with discontinuous functions. And let's start from one example. The right-hand side is defined piecewise. So if you, let me finish it. So if you plot to the right-hand side, it's 1, then becomes 0 at pi. Okay, so if we do it in a traditional way, we'll have to solve it and to get a solution here, then use it to solve this equation in the second piece. But now let's use the Laplace transform. Okay, let's see what we have on the left-hand side. You have remember negative y prime, which is 1. Then this happens to be 0, so you don't have anything else. Just s squared capital Y plus 4y, and then you get the right-hand side. Well, what is the right-hand side? It's go by definition. It's negative e to the negative st g of t, right? But g of t happens to be 0 beyond beyond pi. So it's a finite integral. I mean, on a finite domain. So you can still do it in the usual way. Right, then you plug in the limits, you will have from pi, you get negative s pi over negative s, right? So you get that. And plug in 0, you get a 1 over s at like that. All right, so the right hand side equals this. Okay, so just pretend them like that, right? So you can solve for your capital Y. You move 1 over there. So 1 over 1 minus e to the negative s pi over s squared plus 4. Then you can separate them into 1 over s squared plus 4 plus 1 over s squared plus 4 minus e to the negative s pi s squared over 4 plus 4. And this can be solved using the trig function. I mean, the little y, this would be a trig function, right? And if you remember, this is 1/2 times, this is 2 squared, right? So this will be 1/2 times sine of 2t. And this you can break it into s and s squared plus 4. And you can see this is like 1, this is negative s, and then divided by 4, and then give you 1/4. This is a 1 minus cosine 2t. Right? Okay, how about the last part? That's something we don't know, because we don't have anything like exponential function in our right hand side of the table. Remember our table? Out of e to the at equals 1 over 1 over s minus a, etc. Right? We have exponential function on the input, but we never had exponential function on the output. But now we have exponential function on the output. So how do we do that? Well, we need to build our table to include exponential function on the s side. All right, now let's see. How do we do that? We'll come back to this problem later. Now let's define this so-called step function. Well, actually we do have something on the right-hand side with exponential function. It's here, this guy. This g. And it gives you exponential function on the right-hand side. Right? It's just not so convenient because you have an extra term that you don't want. Right? So let's see, how do we get exponential function only without any extra term? Okay. Then we use something called a step function. Now let's define step function. We call it uc of t. It's just like our last function, but it's flipped. This is 0, that is 1. And this is c, and a positive number. So this function has 0 value below. So this means it's 0 for t is less than c, and 1 for t is greater than or equal to c. Okay, that's called a step function. And let's see what is the Laplace transform of the step function. Right, and you can see it's actually from c to infinity, because below that it's nothing. Right, then you can plug in the limits, and plugging infinity you still get 0. Plugging c you will get negative sc over negative s, but it's in a lower limit, so it's positive. So that's your Laplace transform. So you see, we have exponential function now, and that corresponds to the step function. So we can use this formula to handle this term here. Right? So it means you will have a u pi of t in your solution, because u pi of t would have e to the negative s pi. Right? But we also need to take care of that term, right? So we need to learn how to have more terms than just this s. Okay. But before that, let's see what if you have a general function. Say you have a uc times a general function. Say f of t like that. Then you will see if you integrate this function, this will be cut off, right? It's gone. You only have this part. And this will certainly not directly related to that, because information of the function in the first domain is lost. So you cannot relate them in any straightforward way. But if you shift the function instead of cut it, you will retain all the information like that. So you move the function there, then integrate. Then you can see all of the information of the function is retained, right? So the correct question is not f of t, it's f of t minus c, because if you shift the function to the right, the function can be written as f of t minus c. Right, so that's your original function, and that's your truncated function. Not truncated, shifted function. Alright, so everything is moved to the right, and the space before that will be filled by 0. Then this is related to that this is related to that in a very simple way. Let's just integrate, you will see why. This will be e to the negative sc, then you have uc f of t minus c, and then you have e to the st, and this means it's nothing below c. So you have c, then you have st minus c. Right? Then we can just change a variable. Let me call this u. It's negative s u plus c. Then I have s here. U plus c f of u du, and the u is t minus c, so go back to 0. Then you can factor out e to the negative sc, and then inside it's negative su f u du. Guess what? That's your capital F. So it means this just equal to that times e to the negative sc. Yeah. So it means if you shift a function to the right by c and filling the gap by 0, then the Laplace transform will be multiplied by a power exponential function. So that's what I mentioned earlier. If you have exponential function in S, then it corresponds to shift in T. Do you remember the other pair? It says if you have exponential function in T, then you get shift in S, right? So they come as a pair. All right, so we can use that. So in other words, if you know your exponential function, if you see your exponential function in your function of S, then you can recover the original function by doing the inverse transform of this part, then shift it, and then times UC. All right. So for example, let's see, what is the inverse transform of let's say e to the negative s times let's say 1 over s squared. All right, then we see this guy means c equals 1, so you have start with u1. Then you have to do the inverse transform of this, then you shift it. This will give you a function of t, right? Then you shift it like that. So what do we have? The inverse transform of 1 over s squared is just a t. So you replace it by t minus 1. So that's your answer. All right, that's how you do the inverse transform of exponential function of s times a polynomial or fraction. Okay. Now let's get more preparation before we apply that. If your right-hand side, say your equation the right-hand side is piecewisely defined. You have a, let's say, sine t and t less than 1. Say t when t is 1 and between 1 and 2, and say it's 1 when t is beyond that. Then you have to write down the right-hand side in terms of the step function before you apply these formulas, right? So how do we do that? If you sketch it, you have sine of t, which is 1, then after that it's t, whatever we have, like t, sorry, and after that it becomes 1. So just a piecewise defined. So how do you write on the right-hand side? You start with sine of t, and you have to change it at 1. Change by how much? Well, you change by the difference between the second and the first definition. Why? Because when t is less than 1, this is 0, so you only have that. When t is more than 1, you have this equals 1, so this add that will give you t. Okay? And what do you do for the next segment? Once again you add the change. The change is 1 minus t. Because when t is more than 2, you have this plus that, which will recover 1. Okay? So when you do the when you write down the function in the step function, when you write down the piecewisely defined function in the step function, you write down the sum, and each one is the difference times the step function. Okay? Now let's try more example. Say if your g is say 0 when t is less than pi, and t squared when t is more than pi, then what do? Well, that's pretty easy. That's just equals t squared times u pi of t, right? Because you don't have anything to start with, then you switch to t squared, right? And let's do a harder one. Say you start from 1 when t is less than 1. Then let's say we have a linear growth. So you have t between 1 and 2, then it becomes 2 after that. Right, so plot it will be start with 1, then becomes 2, like that. Okay, so how do you write down the step function? So you start with 1, then you add the step function. Oh, sorry, the c is 1. Then you don't write down t, you write down t minus 1. Right? Then you add another jump at 2, and you don't write down 2, you write down 2 minus t. Okay, so that's your form of g in terms of step functions. Alright, so let's see how do we change this. Let's say if we want to integrate, do the transformation of that function. Okay, then what do you get? 1 would give you 1 over s, and this function, okay, we have to recall that formula. Okay, the formula says the transform of uc of t times f of t minus c equals the original one times e to the negative sc, right? So you can use it in this way or that way. Now we use it to the right side. So to find out the capital F, you need to know what is f, but this f is not just this function. You have to unshift it. Yeah, so if c equals 1, so that's 1, so it means you have to, so let me rewrite this. Okay, so it means if you use it the forward way, you would prefer this form. So you have to, if you start with ft, then this is ft plus c because you have to undo the shift. Alright, but if you go backward, then you recover the little f, then do the shift to the right, and this is shift to the left. Okay, now we can apply this formula. Then this is e to the negative sc, and that's just s. Then you change t to t plus 1, so just that. Then this is e to negative 2s, and you replace t by t plus 2, so this is negative t. Alright, so you will have 1 over s plus e to the negative s out of t equals 1 over s squared. Then you have negative e to the negative 2s 1 over s squared. So that's your result. Okay. On the other hand, if we want to do the inverse transform, you have to use this first formula. Okay, let's see an example. How about just use the one we worked on in the first place? This one here. Oh, where is it? It's gone. It's this one here. Okay. S plus square plus 4. E to the negative s pi s square plus 4. How do we do that? You have to do the partial fraction as usual, and then you have s square plus 4, and if you put 1 here, negative s here, you will see you have s squared plus 4 minus s squared, so it's give you 4, then you just divide by 4, right? Alright, see. So how do you do that? This means you have a u pi, and you have 1/4 Then you do the inverse transform of this guy, 1 over s minus s squared plus 4. But that will give you a function of t, right? You have to replace t by t minus pi, because you have to shift it to the right by pi and by c. Okay, so let's do it. So this is u pi of t times 1/4, and this will give you 1 oh sorry, not 1, this is just t, and this will give you cosine of 2t. So you have to replace everything by t minus pi. Alright, and you can simplify this a little bit, because we know for cosine function, cosine 2t and cosine 2t minus 2 pi is the same. So that's your result. Alright. Okay, that's it for the step functions introduction. Next time we will see how do we apply all of this to differential equations. Okay, that's it.